Thanks for the nice introduction. So today I'm going to talk about models and methods for managing uncertainty in sequential optimization. So this will draw upon several works, and I'll acknowledge my collaborators as I go. So first I'm going to talk about what I mean by sequential decision making under uncertainty. And then I have two active, among other things, I have two very active research projects. I couldn't pick a favorite, so I'm going to give an overview of the two of them. So it will be a two-part talk. In the first part of my talk, I'm going to talk about one sort of challenge in these decision-making problems. That is the chance constraint programming, where we have certain risk or reliability or quality of service restrictions. So that will be the first part of my talk. And the second part of my talk, I'm going to talk exactly about the difficulty with incorporating discrete decisions into stochastic programs, stochastic optimization problems. So first, a very high level, what do I mean by sequential decision making under uncertainty? There are different ways to look at this, but the way I'm looking at it is I have a finite horizon decision making process that decisions are made in multiple stages. And there's uncertainty in certain parameters that also get revealed in stages. So at the beginning, we don't know anything, and we start observing this process that is revealed over time. I'll give some examples in a little bit. And so what we have to decide now is make some first stage, typically strategic decisions at the beginning. And then once we start observing the uncertainty, we make recourse actions or we make contingency plans to mitigate the risk. So I'll talk about a few applications, but actually, there are many applications outside of what I've been looking at. So today I'm going to talk about one application in supply chain, one application I'm getting started on in power systems, and also disaster preparedness. I've recently started looking at these energy applications with my collaborators at Lawrence Livermore and also Berkeley. So one of the most interesting problems, in my opinion, in current power systems research is the integration of renewables into the power grid. So one of the fastest growing renewable is the wind energy. So the goal that Department of Energy set is to have 20% wind penetration by 2030. Right now we are at about 4%. And it is a fast growth. So in the past couple of years we had 35% growth. And some states like Iowa is already at 20% actually. So, so this being a windy city, and perhaps there's a potential here also to reach this goal earlier. So the problem with wind energy is it's highly uncertain and it's intermittent. So we cannot really sort of dispatch it, or we cannot really schedule it and say we will generate this much power from wind at any given point in time. On the other hand, the traditional generators, like the coal-fired generators or thermal generators, they're very slow to start and to produce. So there are a lot of limits on the production levels and also the ramping, how much you can ramp up or down. So those generators are typically committed a day ahead. So there's the day-ahead problem, which I consider to be the first stage problem, where you decide these slow generators to be on or off and have some idea about their production levels. And then the uncertainty is also in demand in first hand. So this is the load in power systems terminology, but also if you have wind energy, that is also another uncertain component. So you have a better idea about the wind levels and the day of the planning. And the second stage problem is now to decide on the economic dispatch, which is how to satisfy the demand or the load for energy by a mixture of our traditional and more renewable sources. So the risks involved over here there are two types of risks that they're opposing. So the first one is if you relied a lot on having wind and the generation turned out to be low, then we might have lower production than we needed. So there's a possibility of loss of load. So we cannot meet the demand. If, on the other hand, we over-generated with our traditional generators and there is strong wind, then actually there could be overloading in the transmission lines. And so the lines can trip, and this could cause cascading outages. So one needs to balance these out in terms of planning how much power to produce. So this turns out to be an complicated stochastic problem. And again, it does involve integer decisions on terms of whether to turn a generator on and off. Another problem I've been interested in through my collaboration with Yicheng Chu, the transportational engineer, is the disaster preparedness problem. We started looking at this problem at the University of Arizona. So he just moved from Texas, where he was active with the Texas Department of Transportation. And this was right after Hurricane Rita. Hurricane Rita hit shortly after Hurricane Katrina. It was fast approaching the Galveston-Houston area. So I put a Google map here. So it was approaching the Galveston-Houston area, and people were ordered to evacuate. So as you can see from the Google map, there's really one way out, one highway out of this area to go into inland Dallas-Fort Worth area. And so because of also the fear about this being as strong as Katrina, people left immediately. And what happened is that something unexpected, the cars ran out of fuel. And a lot of this congestion, this is one of the worst congestions that we have seen. So the third worst traffic jam in history at the time, miles long, 100 miles long jams, and thousands of cars were out of fuel. And that was actually contributing to this jam. So one of the problems in disaster preparedness, this is one example, but in general, is to first before the disaster happens, to preposition supplies and determine the stocking levels of supply. This could be fuel in this example, but in other applications, this is ready-to-eat meals, water, medical kits. And then you have some idea about how bad the disaster could be, so that's uncertain. But once that is revealed, what parts of the network is affected and how much demand is for each product, then the second stage decision is the distribution of these goods to the areas in need. So this is another application that I'm looking at. But in general, what we're trying to decide is at the beginning, we have to make some decisions without knowing exactly what will happen with our uncertain parameters. And once we have a better idea, we make recourse actions. So I'll talk about the standard methodology and some of the challenges that arise with this methodology. So a standard stochastic programming formulation, we denote with omega a random vector with finite support. So oftentimes, throughout my talk, I'm going to assume a finite support. So we have a finite number of scenarios representing what could happen. This could come from a sample, or it could be an empirical distribution based on historical observations. So in the first stage, we make some decisions. I'll call those X. And then we observe the uncertain parameters, the realization. And then we make recourse decisions. So these Y, the second stage decisions, are a parameter of the outcome that we have observed. Capital X is going to denote any first stage constraints we might have on the first stage variables. So I'm going to assume that these are polyhedral, AX less than or equal to B. And we could actually have integer variables here. And then in the second stage, though, in the standard stochastic programming world, we're going to assume that all variables are continuous. And we're going to see why this assumption is made. And I'll talk about how we can lift this assumption. So a two-stage stochastic program, I didn't write it in the two-stage format, but I wrote it as one stage. But as you can see, this has a two-stage structure. So first stage decisions, we're minimizing some first stage cost. Plus expected future cost. So again, the cost could be random in the second stage, so G of omega, subject to some first stage constraints. And the second stage constraints depend on what our first decisions were. And again, this is the most generic format where the right-hand side, the technology matrix, the recourse matrix, and the cost in the second stage could all be random. So this is a two-stage stochastic program. This has been well studied. It's still a very difficult problem, but it's well understood in terms of solution methodology. The most effective one relies on a decomposition algorithm. First, let me give you a deterministic equivalent formulation. So assuming that I have finite linear scenarios, and each might have a different probability, pi of omega, we can write actually one monolithic mixed integer program to model this. So this is known as the deterministic equivalent formulation. So we're minimizing the first stage cost plus the expectation of the second stage cost. So that's the second part. as you can see, we have one vector of second stage decisions for every possible outcome. And then we have the first stage constraints, ax less than or equal to b. And then the second stage constraints have this structure, this sort of staircase structure. And one observation about this is if I fix x, this fully decomposes into a single scenario problem. So I get fully decomposable for each scenario, we can solve its own problem. So this has been exploited with an adaptation of a Bender's algorithm. So I'll give you a review in case there are some students who might not have seen Bender's decomposition algorithm yet. So in this algorithm, it's originally developed by Bender's in 1962 for deterministic integer programs or even linear programs. And then the particular application to this class of stochastic programs was given by Van Slyke and Wetz, and that's typically called an L-shaped method because of the sort of shape of the problem. So here we have a master problem at every iteration. This k is going to be my iteration index. At every iteration, we're solving what's known as a master problem. In this problem, we only have our first stage decisions x and also some expectation of the second stage costs only. So my thetas are going to be the cost of the second stage, expected cost of the second stage for a particular scenario. And that is my best approximation so far. So it may not be a correct value. We have these set of constraints. I'm superscripting that with the iteration number because it's going to depend, the constraint set is going to depend, it's going to grow with iterations. So we have the original constraints, and then we're going to add some optimality, what's so-called optimality and feasibility cuts to this problem based on whether our guess at the current iteration on the first stage solution x was a good one. So I'm going to also review this in a little bit so I can talk about how this may or may not work in more general settings. So in the subproblem, we have solved the master problem at the current iteration. We got a first stage solution x and some guesses on our second stage cost theta. We feed this x into a subproblem. So these subproblems are going to be one for each scenario, and they're going to get their own cost and technology and recourse matrices and so on. So notice that it's very important to assume that the second stage variables are continuous here, because what we're going to do is we're going to solve this problem. And if this problem is feasible, but our guess for its objective function value, theta j, coming from the master problem, does not match with the objective function value we get by substituting this variable in, then that means that our guess for the objective function is wrong, so we need to add an optimality cut. So we need to get a better guess about our theta function. And that comes from the dual. So the dual, once we solve this as an LP, we get a dual vector uk and omega j for each scenario. And so the dual is a maximization problem, and we can say that the objective function value of this scenario should be at least the dual objective function for this particular scenario. So this is an optimality cut. And again, it heavily relies on the fact that I have an LP to solve, and I get the dual from this LP. If the second stage problem becomes infeasible for this particular choice of first stage decisions, that means we shouldn't choose these decisions, because the stochastic program assumes that for every first stage decision, I need to have a second stage feasible solution. So then a feasibility cut is added, and that is again because this subproblem is infeasible, the dual is unbounded. Or we can show that the dual is unbounded, so we need to eliminate that solution from future iterations. So that's how the master problem gets these cuts along the way, and at the end it is shown that this would converge. So this is a review of what we know about the stochastic programs, stochastic linear programs or stochastic programs with linear continuous variables in the second stage. So the challenge just that I'm interested in the first part of my talk, in one of my active projects, I'm interested in the problems when we have risk, reliability, or quality of service restrictions. So we know that we may not be able to meet every scenario, but we need to meet a good number of them. So 90% service level or 95% reliability. So we want to be feasible in most of the time. So we're going to model these as chance constraints, and the problem with this is it becomes, even if you have a linear program, the chance constraint linear program becomes a non-convex problem. So these are going to be much more difficult than the traditional stochastic program. So that's one difficulty I'm going to address in my talk. And in the second part, I'm going to talk about having integer variables in the second stage. So as I showed you, the algorithm that is working for the current two-stage stochastic programs heavily relies on second stage being continuous and a dual becoming available. When we have integer variables in the second stage, we cannot talk about the dual, or at least the dual is not as well understood. So we need to do something to convexify the second stage problem. Again, a source of non-convexity that we need to address. And underlying both of these lines of research is the fact that we oftentimes need many scenarios to represent what the uncertain parameters may be, at least approximate what they may look like. So I'm going to be talking about a very large scale problems with lots of scenarios. Okay, so let me first talk about the two-stage chance constraint programming work that I've been working on. So some acknowledgements. This is what I've got my career grant on, and it draws upon some earlier work I've done. Actually, this was a grant that I got from Manufacturing Enterprise Systems and multi-item, multi-echelon production planning. I need to acknowledge some of my collaborators. So I'm going to be mostly talking about this latest work that I'm working on with my PhD student Xia Liu and my collaborator Jim Lutke in Madison. But I'm also going to be drawing upon some of my work, earlier work in chance constraint programming. And also some of my work I did with my former PhD student Minjia Zhang. She's now a faculty at University of Alabama. And my master student, so one master student did a thesis with me, and this is also based on her work. All right, so let me first talk about what we refer to as a static joint chance constraint program. So we are, as I mentioned, we're given a risk, a reliability, or a quality of service threshold, tau, that is an acceptable service level. And what we're trying to do is we're trying to make some decisions. I'll call that X and Y at this moment. In such a way that the second stage is feasible. So what happens here, unlike what I showed earlier, is we make some decisions, and then we observe the uncertainty, and there's sort of no recourse action. That's why I call it a static model. So it looks like the earlier model I had, except that y is not dependent on omega, so we are not updating our decisions as the uncertainty is revealed. And again, what is different here is that we'd like to have the probability of being feasible as with respect to the second stage decisions to be exceeding the threshold that we've set as our risk level. And again, just like before, I'm going to assume that there are some first stage constraints that the x must satisfy and y is continuous. So before I started this work, I would say that most of the chance constraint literature focused on this static model. So it started with the work of Charnes and Cooper in the 50s, where they looked at individual chance constraints. So these would only contain a single row, not multiple rows. Then joint chance constraints were looked at primarily by Prekopa, but there's some early work in Miller and Wagner. Here they're assuming a very specific distribution so that the problem can be rewritten as a convex problem. So in my talk, I won't be assuming making any assumptions about the distribution. The non-convexity of chance constraint problems have been shown, the feasible region, how it becomes non-convex even in the linear programming, chance constraint linear programming. So I've looked at some valid inequalities for random right-hand side case myself, and again, Jim and Ricardo Fukasawa has some work on these sort of problems. And there's also the extension to random technology matrix on right-hand side. So Jim has some work on that, and there's some work by Lewis and Teimo. But I would say most of the work is focused on having no recourse actions, or Jim has a model that can be seen as a recourse action, but here he has no costs on the second stage. So what I was interested in, just like in standard stochastic programming, why don't we allow our decisions to be adaptive to the realization of the uncertainty? So, so I'm going to talk mostly about a two-stage, but I'm also going to show some results about multiple-stage chance-constrained programming. So here what we're allowing is there are some decisions that we have to make here and now, and then we observe the uncertainty, and then we need to take some recourse actions based on what we've observed, how bad the outcome might be. I'm going to assume in this part of my talk, just like in the introduction, that the second stage variables are continuous, so I'm not going to allow any integrality here. And the two-stage chance constraint program, again, it's going to look similar. What is different here is that I'm allowing my second stage decision to be adaptive to the realizations. Again, for simplicity, I'm going to assume that all the samples, I have an IID sample, every scenario is equally likely. What I said, whatever I said can be extended to the case where I have different probabilities for each scenario. Okay, so this is just to address the question more sort of managerially, what is the benefit of making dynamic decisions adaptive to your realizations as opposed to a static decision here and now? So this is the application I looked at in supply chain. It's a multi-stage inventory control problem. What we're trying to decide at every stage is how much order, how many units of order we should place. We don't know the demand for sure, but we have some idea about its distribution. So in the earlier models I talked about in the literature, what you would do is you would set up a production plan for whatever your horizon is. So if I'm making a weekly plan, I will decide my production or order levels over the next 7 days. And I won't touch those decisions, even though I see that, okay, my demand is actually pretty lower than I expected and so on. So that's a static model. And in the dynamic one, just like I said, I allow myself to update my decisions. If I started seeing some low demand, I adjust my orders in the future period so that I don't order as much. So that's static versus dynamic. Here's a chart that I have comparing the costs in our test instances. So in the x-axis, I will have the service level. This is the threshold that has been set. So one here means 100% of the time I should be able to meet the demand that I face. And we plotted it all the way up until 50% service level. And on the y-axis, I have expected costs. So looking at all the possibilities, what our expected costs will be, depending on our policy. So the red line here is the static model. Again, we make the decisions a priori and we don't update them as time goes on. And the blue model is going to be the dynamic model where we allow to update our decisions. Here we have to be careful about what's known as the non-anticipativity. So we cannot make different decisions in different scenarios if we don't know exactly which scenario we are in. So what we observe from this chart is that for this class of problems, there's a significant saving for allowing yourself to make your decisions adaptive to what you observe. So this is not too surprising. What I found surprising here, not surprising, but interesting here, is the slope of these functions. So you can see that if you sacrifice a little bit from your service level, if that is allowed, you can get greater cost savings with the dynamic model than if you were to do that with the static model, because of the sort of the feasible region being much more restricted in the static model when you cannot update your decision, so you have to stay feasible most of the time, no matter what happens. So if you have the flexibility to update your decision as time goes on, we would propose the dynamic model as opposed to the static model. So how would we go about solving the dynamic model? I'm going to switch back to the two-stage world. So again, we have our decisions X and Y. The deterministic equivalent program is going to look similar to the two-stage stochastic program, except for one difference here. So originally, my decision variables are X's and Y's and vectors. But we're going to have these new decision variables, Z's, that are binary. So this is where the integer variables come into play. So we need to introduce these variables to tell us which scenarios will be met and which can be violated, because now we don't have to satisfy all scenarios. So Z1 is going to be 0 if scenario, ZK is 0 if scenario K is satisfied and 1 otherwise. So you can see that when Z is 0, I recover my original constraint inside the chance constraint, so it has to be satisfied. If Z is 1, this m is going to be a vector of very large numbers. So it becomes a redundant constraint. I do not need to satisfy it. So there are two problems with this formulation. One is that it's very large scale. We have many scenarios. And the other problem here is these big M's. So this big M is a sort of a dreaded formulation in integer programming. So if you show a formulation to an integer programmer with big M's, a couple of them would be okay, but this has a big M in every single constraint. So this is, we know that this is not going to perform very well, even though if it were a small formulation. So, so we try to both address the fact that it's large scale, try to decompose it again using the same observation. If I only knew my first stage decision X's, and if I knew which scenarios I needed to satisfy, then I can fully decompose the problem and solve the single scenario subproblem separately. So if I wanted to parallelize this, I could do that. So that's what we're going to utilize here. So we're going to talk about a decomposition algorithm for two-stage chance constraint program. As a sort of in the skeleton, it's the same as the Bander's method, but we have to worry about the optimality and feasibility cuts. So we have second stage costs. So our recourse actions have different costs depending on what the decisions are. And again, because it's chance constraint, we do not have to satisfy every constraint. So we need to worry about how to make correct feasibility and optimality cuts compared to the earlier Bander's method that I talked about. So our goal would be to develop valid feasibility and optimality cuts to the master problem of two-stage chance constraint. So overall, it's a similar algorithm. We still have a master problem that has the first stage decisions X, the theta, these are my approximations of the second stage value function, and we'll have these Z variables, the binary variables. So this is really the chance constraint, assuming that I have equally likely scenarios. At most, P of them can be violated. So, so that's the chance constraints equivalent. Z's need to be binary. I have one for every scenario. X needs to satisfy first stage constraints. And then I have a collection of cuts in the X and Z space. So these are the feasibility cuts. So I need to make sure that if I'm saying a scenario needs to be satisfied, that X actually gives a scenario that can be satisfied. And there's another set of constraints here, and this is going to grow at every iteration. And this is going to be a function of X's, Z's, and the thetas. And we call these the optimality cuts. So again, this is a cut on the guesses, our current guesses on the value function of the second stage. Another notation I'll introduce is this polyhedron PK. This is in the X space, so X needs to satisfy its own constraints. And it should be such that there exists a second stage solution satisfying that scenario's second stage constraint. So PK is going to be that polyhedron for every scenario. So the optimality cut generation. Suppose we solved the master problem and we got a solution X hat and Z hat, but it has an incorrect estimate on the second stage value function, theta hat. So what this means is if a solution is feasible with respect to a certain scenario. So what it says is zk hat is 0. Remember, zk being 0 means that that scenario must be satisfied. Scenario k must be satisfied. So we actually solve that scenario subproblem. Now, this is only in the space of y. X is given as an input from the first stage problem. I'll call the optimal objective function value yk. Again, this is a continuous linear program. So we substitute that x hat in, and we actually see if this is really feasible. If it is feasible, then we get the dual function uk. And then we need to add an optimality cut if our guess for the objective function value coming from the master is different than what we got by actually solving the problem for this particular choice of x. So if our guess was wrong, it's smaller than what it needed to be, this is the optimality cut we add. Again, it's going to look very similar to the Bander's optimality cut. The way it works is when zk is 0, so this term disappears, and that's just your Bander's cut. So you have to satisfy this scenario if zk is 0, so you have to pick up its correct cost coming from the dual. Whereas when zk is 1, this m is going to be, again, this big M that is large enough that this becomes a redundant constraint, and we may not be satisfying this constraint, so we shouldn't be picking up its cost. So this is how one might implement a decomposition algorithm to add the optimality cuts. I'm going to come back to this because I've got rid of the size of the problem by decomposing it, but I still have the big M. So this is going to be something that I'll come back to in a little bit. So we're not too happy about it, but at least we have some way to decompose the problem. If we plug in this zk being 0, which says that the scenario needs to be satisfied, but actually the problem turns out to be infeasible, then we have to add feasibility cut. So that's the feasibility cut. And this is actually similar to Jim's earlier work, Jim Lütke's earlier work. So we detect an infeasibility, and this is an infeasibility in the sense that we have a scenario that should be satisfied, but it's violating. It's not an element of the set PK. So again, we solve an optimization problem. This time it's in an expanded space. So in X and Y space, X needs to satisfy the first stage constraints, and Y also the second stage. For a given alpha, I'll come back to this alpha in a little bit. So we minimize this alpha X. We're going to get our alphas from where the infeasibility comes from in the problem. So we do a quick sort of these objective function values. Sigma is going to be a permutation that is the sorting of these objective function values. And so we're going to select a subset of these scenarios from the first P. Remember that we cannot violate more than P scenarios. So that's why I select a subset of this P scenarios that give me the highest possible value for H. And there's this so-called mixing inequality that is guaranteed to cut off this feasible solution. I'll explain how this works. So the cut looks like this. It's in the space of X and Z. And as you can imagine, we have exponentially many of such cuts because we have exponentially many subsets that we can draw upon. So what this says is the following. So suppose we have a solution. It's infeasible currently. What that means is we have an alpha X currently that lies between two values, let's say Tj minus 1 and Tj. And what we need to have is, because alpha X is smaller than what it needs to be, so H optimizes what alpha X needs to be for every scenario. So what this says is that alpha X is actually smaller than what it can be in an optimal solution. So those scenarios should be violated. Their Z values should be 1. And so if you plug in until j minus 1 scenario, these need to be a 1. So this is sort of a sum where things cancel out, and you get a constraint that says alpha X is greater than or equal to HTJ minus 1. Right? So HT1 minus HT2, HT2 minus HT3, and so on cancels out, and you have alpha X is greater than alpha Tj minus 1, so the current solution gets eliminated. And so this is a valid inequality, and it eliminates the current infeasible solution. So this is a combinatorial cut that is different than the traditional Bender's feasibility cut. So remember that this is with a big M optimality cut. So we tried we tested these instances on the simplified disaster preparedness problem. This is the hurricane evacuation problem, where we didn't make the location decisions, just the stocking levels of the fuel and how to distribute once the disaster hit. In this column, I described the instances. So M is going to be the number of scenarios. So we tried somewhere between 300 and 500. 1 minus tau is our service level, so we have 90 or 95% feasibility requirement. N1 is the number of first stage decisions, so stocking levels at, say, 5 or 10 fuel stations. And D is going to be the demand areas, so N1 times D tells you an idea about how many second stage decisions I have. So as you can see, this is a moderate size problem, so 200 second stage decisions for the largest one, and 10 first stage decisions for the first stage in the largest instances. So this first two columns here is going to give the performance with the deterministic equivalent formulation, so the single mixed integer program that solves this. I'm going to report three things: the time to solve the problem, the number of solved instances, so every row is going to correspond to 5 randomly generated instances that I'm averaging over. And the gap is the end gap, so we have an hour time limit. If the algorithm didn't stop within an hour, we look at the end gap, how much far we are from an integer optimal solution. I call this the basic decomposition. Again, this is where I can decompose the problem, but my optimality cuts contain the began term. So time to solve this problem. As you can see, the time grows quite fast for the deterministic equivalent formulation. So as I go to the 400 scenario or 500 scenario for the larger problem size in the second stage, I'm hitting the time limit in all my instances. In the smaller problems, we have better success, although some of these, so for example, for this instance, one instance didn't solve within the time limit, and it had a 1.3% optimality gap. With the basic decomposition, we're actually able to solve more problems, many more problems than we were able to solve within the time limit. When we are able to solve it, it's about 1/4 of the time. And there are small end gaps when we are not able to solve. So this was an okay performance, but we noticed that this began is again slowing us down in going to much larger number of scenarios. So we wanted to do something smarter than the began cuts.
Quick question about the
Sure, sure.
What's the scenario?
So the scenarios here would be the demand. So based on the severity of the disaster, how much demand I will have in each sort of demand area. Exactly.
So what's the dimensionality of the scenario?
In this one, 20, I think this was when we had right-hand side randomness only, so 20 demands at just the second stage. So in my collaboration with Yi Chang, he had a traffic simulator, so he would randomly assign initial fuel levels and run the simulator. That particular problem was easy because there's only one way out, so we would get a guess on where people would run out in the geographic map in terms of their fuel levels. So yeah, so the randomness is only in 20 parameters, and the largest one and 10 in the second one. Okay, so we wanted to do something better with our optimality cuts. So here's the idea that we have. So again, this alpha, just take my word for it that when we have an infeasible solution, we know exactly how to pick this coefficient vector alpha. And then we're going to solve a similar optimization problem that we had before, Vk of alpha for every scenario. Again, in the space of x and y variables, where we're minimizing the original cost. Previously, we didn't have the second stage cost at all. Second stage cost plus this alpha term and the x, and the second stage constraints involving x and alpha. We have an observation that the second stage value function, theta k, based on the way it's constructed here, remember that theta k would be the optimal value g omega k y. So that is greater than or equal to Vk of alpha minus alpha x for any given x or any given alpha. So what we do is, when we encounter a solution, we select a subset of scenarios that is satisfied in a feasible solution. Note that we need to have m minus p of them. We can violate at most p scenarios. And again, we solve this second stage problem, the original second stage problem, and get the dual vectors. So the improved optimality cut looks like this. This is an aggregated cut. So it not only uses the information that is coming from the second stage function, but it's also using the information that we can violate at most p scenarios. So it's a weighted sum of the second stage value functions. So this is what it looks like. Again, let's compare it with the Bender's cut. So if all the scenarios that we selected in this set S are satisfied, I'm going to get a zk of 0 for all of them. This term is going to disappear, and I got my aggregated Bender's cut. So this is the Bender's cut I would have gotten if I had to satisfy these scenarios. But when any of the zk's are 1, what this does is it picks up a coefficient here that is a v hat. V hat is a minimum of the v's here, the optimization problem, that are among the unsatisfied scenarios. So this is a much smaller set. I need to solve this problem only for a small fraction, whatever my tau value might be, 1 minus tau fraction of the scenario. So this is a many smaller problems to solve, much smaller problems to solve. And I pick the minimum one. What this says is that if this scenario is not satisfied, some other scenario needs to be satisfied that is not currently in my set S. And so what I can do is I can put the small as such possible to keep it feasible, make the cut feasible, valid. So this is an improved optimality cut that we've tested. So this is, I guess, fresh from the computer lab. So this is ongoing work, and my student Shia finished these runs recently. So this is going to be an average of 3 instances, not like the 5 that I had before. And we are actually scaling these problems up. As you can see, I'm increasing my second stage decisions and the first stage decisions. And I'm looking at 10 times more scenarios in this class of instances. So now I'm going to compare the deterministic equivalent, the basic decomposition, the standard one you would come up with, and the strong decomposition. This is the one with the improved cuts. I'm reporting similar data. In order to fit it into this table, I'm going to report the gap in red and the time to solve in black, and the parentheses, the number in the parentheses, the number of solved instances out of the 3 that I tried for every row. So again, the deterministic equivalent formulation begins to fail. So in these very large instances, actually it wasn't even able to solve the linear programming relaxation. It ran out of memory. In the smaller problems, so as you can see, if your problem is small, maybe the deterministic equivalent formulation is good enough. As it grows larger, if it's able to solve it, it could be competitive, but there are times when it is not able to solve to optimality within an hour and with a high end gap. Whereas our algorithm scales much better, so it has almost a linear growth with number of scenarios because we benefit from the decomposition of an algorithm. And the big M method, as we were fearing, wasn't doing so well with these large number of scenarios because we have so many big M terms, even in the optimality cut.
So the chance constraint aspect of the problem doesn't hurt because you have a chance constraint at the second stage. If you're observing linear growth, that's linear growth in the standard system.
Exactly. It was a similar performance with that. So
my question then is, are these chance constraints easier to satisfy? That's why you're not getting the linear speed up, or is it even your problems, you have a hard chance constraints to satisfy? Push the level up to 0.99. Like
actually,
what happens?
interestingly, the problems get easier. So this one I selected. I think we were talking with Andreas as well. The problems get easier when when it is tighter. So when you have lower level of violations. So when you have 99%, it's so restricted that it's almost the stochastic program that you had to satisfy all of them. The problems get harder as you lower the service level. Because now there's this combinatorial aspect of you can violate many more combinations of scenarios. So our observation in these classes of problems were getting more difficult when you lowered the service level. The higher service level brought us similar to the normal stochastic programming when you have to satisfy the constraint. But yeah, we were pleased with these results that we can still get that linear growth despite the fact that we've added integer variables, but we've added them into the first stage. So this part of my talk still relies on second stage being continuous and some information about the duals being passed over. So I have, I think, 15 minutes to go through the second part of my talk, but before I move on, are there any questions on the chance constraint side? Okay, so I'll probably go through a little faster. So what I was able to talk about is this new class of models, multi-stage. I talked about the two-stage version because the decomposition works for that. For the multi-stage version, the decomposition needs to be done in a nested fashion. We haven't tested that yet. Like I said, in our test instances, we saw a linear growth, at least in the problems we looked at. Some of the results I didn't get a chance to talk about. We actually have another model, especially probably applicable in disaster response, where we have also what we call recovery operations. So right now what we say is if we don't meet a scenario, we just don't do anything about it. And we try to meet the scenarios that we have. So in this model, we also have recovery operations. So we have two types of operations, normal operations and the recovery operations. So when something really bad happens, then we need to fix that problem as well, but maybe we have more time to fix that problem. So it's almost a three-stage problem. A lot of the algorithms I talked about extends to that model as well, with some work. So again, with my students Minjao and Samya, we looked at the multiple stage version, and we developed branch and cut algorithms for that. And this is an active area of trying to incorporate risk into dynamic decision making. So there are some models in dynamic risk-averse optimization and robust optimization. Actually, we were asked to compare our models with such models. They're not easily comparable, but at least what we observed is that if you really have such a risk constraint, and then our model is the one that is giving you the minimum cost at that guaranteed risk level. So in the dynamic risk-averse optimization models, if you're familiar with it, we cannot really guarantee a certain service level. We can just try to minimize that risk. And robust optimization tends to look at the worst case and try to satisfy scenarios in the worst case. So just a brief overview of my second project, I think, in the next remaining time. So here the goal is to incorporate discrete decisions into the second stage. Like I said, a lot of things will not work when we are not able to get the dual information. So this is another line of research that is joint work with Surajit Sen. And actually, a year and a half ago, I think I was here talking about this paper with our joint student, Dinakar Gade, who now graduated, and Surajit. So with my most recent student, we were able to extend it significantly. So I'm going to focus on this, at least give you an idea about what we did here. Okay, so again, now forget about the chance constraints. We're back to the two-stage programming where we have to satisfy the second stage scenario no matter what. But I'm going to assume, at least in this talk, that we have discrete choices in both of the stages. In fact, I'm going to assume pure integer programs in both stages. So first stage problem, now I'm going to give it in a separate two-stage fashion. So in the first stage problem, we minimize the first stage cost plus the future expected costs subject to its constraint, but now again have integrality restriction, not just binary, but general integer variables. And for a given realization scenario, we have the second stage constraints. Again, I'm going to now require that second stage decisions be binary and general integer altogether. Capital X is the first stage feasible region. Y of x and omega is the second stage for a given x. So again, I already talked about the Banders or L-shaped method for continuous second stage. So this is what the literature looks like when you go to integer stochastic programming. So these are all papers that looked at different assumptions on the first and second stage variables. There's no one algorithm that necessarily, a decomposition algorithm that solves any class of stochastic integer programs. It depends where your binary variables are, where your integer variables are. And so the work that I've done and presented here earlier assumed a binary first stage and general integer second stage. You will see that assumption in a lot of the work. There are two papers that focus on general integer in both stages. I'll give a little overview of that. And so this is what the literature looks like in terms of the solution methods developed. The closest papers that are related to what I'll talk about is the recent work, Kong and others, and Trepp and others. But they have a strong assumption that the technology recourse matrices T and W and the cost has to be fixed. So that is shared across the scenarios, so the only randomness is on the right-hand side. What I'd like to be able to develop is an algorithm that does not make such an assumption. So this is where we deviate. And the Caro and Tind algorithm, this is close in assumptions to what we do, but this is a conceptual algorithm. So to the best of our knowledge, there's no implementation of this algorithm. It's just to show that a finitely convergent decomposition algorithm exists. I won't go to the details of it, but it relies on this thing called gamma recuts. And that's another thing I talked about earlier. So what is a gamma recut? If you haven't seen it, in a two-dimensional integer program, I have these two constraints. The feasible region is the red dots. And what we do It's solved the LP relaxation. So suppose that blue line is my objective. What I got is this optimal solution to the LP relaxation. X1 is equal to 2, but X2 is fractional. In fact, if I look at my simplex tableau, I'm going to get this source row. So X2 is equal to 2 over 5, and I have these slacks. So S1 and S2 are the slacks of these two constraints. So Gamma cut is actually very easy to explain. So you take the source row from your simplex tableau. This is written in Schwatel form. You take the coefficients from the simplex tableau, and you just round them down and change the equality to a less than or equal to type. So this is how the Gamma cut works. So Gamma showed that this is a valid inequality. And so if you look at this rounding down operation, the Gamma cut looks like this. If you substitute back for the slack of the second constraint, 2 minus x1, x1 plus x2 less than or equal to 2. So that's that. And we got the convex solve. Of course, in this one, it's small enough that I got the convex solve of the feasible solution. But Gamma showed that for any deterministic IP, this sort of cutting plane algorithm is guaranteed to find the integer optimal solution in finitely many steps. So what one can do then is to do this iteratively and solve the problem as a linear program, because now if I solve a linear program, I'm going to get an integer solution immediately, and then I can get the dual from it and pass my optimality cuts and so on. So again, so the challenges we are facing is to develop a finitely convergent algorithm. And some of the problems, again, for a given first stage solution, what I got is an IP, deterministic integer program, but I plug in that first stage solution. I know that I can do a finite Gamma cutting plane algorithm, but if I do it to completion, it is a finite time algorithm, but it takes a while. So we don't want to do that to optimality. And another problem is that in my earlier work, we assumed that the first stage is binary. So binary problems has this nice property. The lifting of the binary variables is easy. So I develop a Gamma cut for a given x, but I need to make that cut valid for any x that could have been passed down from the first stage. I'm going to show that in a little bit. So so that's called the lifting problem. That's easy to do for binary programs, but general integer lifting is known to be non-convex, again, non-linear problem. So the goal is to lift the Gamma cuts that are valid for a given x to any x when x is general integer. And what we want is optimality cuts that are affine. So I can solve a linear program or a mixed integer linear program in the first stage. So we're trying to get Gamma cuts in the form beta y less than or equal to beta 0, where beta 0 is an affine function of x. So what do I mean by lifting? Just a quick example. So 2 first stage variables and 4 second stage variables, all of them are integer, and y0 is the objective function of the second stage. This is actually not stochastic. It's a one scenario deterministic problem, but just to show you how the decomposition works. So if we solve the linear relaxation, we get a solution, say 5 and 5. And then the Gamma cut we generate for the second stage will look like this, plugging in the values 5 and 5. So this inequality is valid for this particular x, but it's not necessarily valid for any x that could have been feasible. So this is a plot I projected so that I can draw it in 2 dimensions. I projected into the y1, y3 space. So these are the feasible points in the y1, y3 space. Suppose y2 and y4 are 0 and x is 0, 0. So the cut that we generated, so plug in 0, 0 here, would correspond to this blue line over here. It's going to cut down these feasible regions. So it's not valid for any x. Assuming x is equal to 5 and 5, plugging it in and generating a Gamma cut is going to violate other possible solutions. So this was a problem we had to deal with. So what we did is to come up with a parametric Gamma cut. So it's going to now, the cuts are going to be a function of x's that is valid for any first stage variables. So again, looking at the same picture, when x1 and x2 are 5 and 5, we're going to get the cut with the right-hand side of 13, as you can see. But when they are 0 and 0, we're going to get this lifted cut. So I lifted that cut for this particular solution, so it didn't cut away any feasible points. So that's the goal that we'd like to do. So here's the idea in one slide in my remaining time. So so the idea is that we solve the linear relaxation of the first stage. We get a basis. So this is from the simplex tableau. And in the second stage, we look at the basic variables from the first stage. So B1 through B1 through B1A, let's say, are the basic variables in the X space. And we look at the corresponding columns technology matrix that gets multiplied with the X's because the other ones are they're non-basic, they're fixed to 0. We solve one linear program, a linear relaxation of the second stage problem. Then we get our Gamma cut from the source row given by this sort of set of equations. So here you see a basis inverse that corresponds to the basic variables from the first stage and the corresponding technology matrix elements and basic variables from the second stage. So note that this inversion is much easier than inverting the entire deterministic equivalent formulations. It only depends on one scenario and one basic variable. And there's a closed form expression. This is an easy matrix to invert. So we have a closed form expression for this inverse, and it involves A inverse and double inverse, which we already have from our linear programs that we solved earlier. So we can actually do this computation in an efficient manner. And we can get a cut that is dependent on the first stage that is valid for any first stage. The decomposition algorithm is going to be similar to Bender's. But the only difference, again, we have the first stage problems with the original cuts and the optimality cuts. That is similar. I won't repeat this. The only difference from the earlier method is that the sub-problems, they keep changing, that we keep adding Gamma cuts, parametric Gamma cuts to the second stage to approximate the integer program as a linear program better. But at every stage, we're only solving 2 linear programs, one without the Gamma cut and one after the addition of the Gamma cut. So here's a picture of the algorithm, and just a little time, so I'll just give you some computational results on some standard test instances that we've tested on, so the details are not very important. What's impressive here is that the BCDG is our algorithm. So my student Minja implemented this purely in C++. There's no help from Cplex at all. The reason for this is we needed to have a lot of control over how which simplex method we chose. So we needed to use a lexicographic dual simplex. So we need to have a lot of control about the branching decisions and what we do. So she implemented the whole thing in C++, the simplex iterations, the branch and bound. And we're going to compare that with Cplex, so with all its bells and whistles. So Cplex D is the default Cplex, even the sort of all features are enabled. We also, to be fair to us in a way, we also tried it with just the Gamma cuts because that's the only technology we are using. So that's Cplex, and Cplex D is the default. Clearly, this being just the C++ implementation, we are only able to test it on up to 200 scenarios. After that, we are hitting the time limit as well. But actually, I think we can grow up until 500. I selected a few instances here. Again, average of 5 instances. I'm also reporting the number of cuts that we are adding, the branch and bound nodes, percentage gap, just like before I had, time and the number of solved instances. And BCDG is our algorithm implemented in C++. Again, as you can see, it's significantly smaller solution time compared to the state-of-the-art mixed integer programming solver, Cplex, hitting the time limit in all 5 instances for this relatively small problem with 200 scenarios, whereas we solve these problems in 20 seconds. So ideally, in the future, we'll have implementation be tied to the Cplex, and we can solve much larger problems. So I'll quickly skip the summary and give some ideas about my future work. So ultimately, what I'd like to have is one sort of decomposition algorithm that can handle mixed integer variables in both stages and 2-stage stochastic mixed integer programs. Again, in the chance-constrained problems, we know not too much about having integer variables also within the chance constraint. I have some work with Jim and Yongjia Song on incorporating integer decisions into the chance constraints. I'm very much interested in the applications, so wind integration is one application I'm currently working on, stochastic or chance constraint version. And another recent topic, I have a visitor coming, working on multivariate CVAR problems, so I also like to model alternative risk measures besides the chance constraints. So that's one of the areas I'm beginning to work on. So that wraps up my talk. Thank you for attending. Any questions? Questions? Mm-hmm. Yeah. Mm-hmm.
You solve the relaxation problem.
Mm-hmm.
That's your, let's say, think about it since before. You get an
Mhm.
optimum basis
Mm-hmm.
to solve the basic relaxation.
Yes.
From there, now that's as a fraction solution.
Mm-hmm.
Going back and looking at only problem with one scenario
Mm-hmm.
for which you actually the corresponding excess fractional and corresponding y or
Exactly.
and or y
Mm-hmm.
fraction.
Mm-hmm.
The question I have for you is in terms of the construction of the new basis
Mm-hmm.
from which you're going to extract the boundary cut.
Mm-hmm. Okay, so Mhm.
Technical point of view.
sure. So in the first stage, we solve an LP also. So even if we are doing a branch unbound, we have these LPs that incorporate the branching decisions, and so they're going to have a list of their own sort of Gamma cuts and optimality cuts. So we take that basis. So that's my A matrix, and then plugging it in and solving the second stage problems for each scenario, we have their basis. So that's the W that I had. And then we construct this. So this would be what the parametric Gamma cut is coming from. So it's a subset of the deterministic equivalent constraints. Mm-hmm. And yeah, as we discussed earlier, it's not going to.
Full row rank.
Mm-hmm. Exactly. We show that there's going to be a valid basis that we can exactly. We
so
have
no
that
matter
proof.
how you solve the problem, as long as you have a simple you have a vertex solution,
Mm-hmm. Mm-hmm.
there's a corresponding basis
Mm-hmm.
whose subset of rows and subset of columns.
Mm-hmm. Is
give
going
you
to
a
be
valid
the
basis
valid,
for this.
exactly.
There's a valid basis here. And that's
Exactly, because that's where sort of this fractional y came from. We substitute this particular x, and that's where this fractional y came from. So we show that this is a legitimate basis, and it's going to have full rank, and it's going to cut off this current solution.
And is this idea of generating cuts like that new? Would it appear?
The Gamma cuts have been around, but to use it in a decomposition context, and we actually have I didn't talk about it, but we have a proof of finite convergence. So the fact that this will actually eventually converge finitely is new. But yeah, Gamma cuts have been around. We're utilizing the fact that it is finitely convergent for a deterministic IP to be able to use it in a decomposition framework.
So what you're really saying is that if you look at the deterministic optimization problem you're talking about,
Mm-hmm.
if you look at it from a pure IP perspective, the cuts are going to involve all the variables. Can
Exactly.
potentially involve all
It
the
could,
variables,
exactly.
x and y's. Because if cuts are generated in this way, you maintain the decomposition structure.
Exactly.
And
Mhm.
you still get finite convergence.
Exactly.
So
Mhm.
there's this block decomposition of the stochastic program
Mhm.
nicely lends itself to
This sort of a decomposition. And this actually is new even in deterministic IPs if you wanted to do a decomposition. So to make the optimality cuts valid when you have your first stage variables that are general integer, it wasn't very obvious or clear.
Okay, so thank you very
Yeah,
much.
thank you.